Hello and welcome to Tea Leaves Programming. Today we are programming like it's 1979. We are doing Haskell for Dilettantes, continuing our sojourn through the Data 61, NICTA, System F, whatever you want to call it, FP course. In our last episode, we completed the optional module, and today we are going to go on to the list module. So there is a lot going on in the list module, and these functions that we're going to implement today are going to run the gamut from completely abstract kind of what does this even mean functions to things that are fairly concrete and practical. Something I may try and do is to implement some of these functions in multiple ways. And I'll talk a little bit more about that as we get into it. Let's dive in. So before we do anything else, let's look at the definition of the list type. This definition is not using the built-in Haskell definition of list, but it is, I'm going to use a fancy word here, isomorphic, the same shape as the built-in definition of lists, or the definition in the data list module. So the terminology and the actual constants here, or labels and names, the naming is different, but the implementation is effectively exactly the same. So we have here our data type list, and a list is one of two things. It is either nil, the empty list, or list T is some item of type T, and then that, I don't know if you can see what I'm highlighting there, the colon dot, instead of just a colon or a comma, they're using colon dot in this implementation, appended to a list. We saw lists in some of our previous episodes, and the syntax was a little different, and it's going to be a little different here because we're using this custom type, but the concept is exactly the same. I'm going to mention aspects of Haskell right now that I'm not going to dive into until we need them. So first of all, we have this interesting thing, the list of integers from 0 to infinity. What the heck does that mean? How can we have a list that is infinite? Well, this has to do with one of the more unique aspects of Haskell. Most languages that you and I have used, I would guess for most people, almost every language, evaluates things in what's called a strict fashion, which means if you have some data structure that you're operating on, you're going to evaluate the entire data structure. Haskell has what we call lazy evaluation. In fact, my understanding of the history of Haskell is that playing with lazy evaluation was one of the major motivating factors behind the design of the language. Something that, see, I'm starting to go into it. I don't really want to go into it. The basic idea at the 50,000 foot level is that Haskell only evaluates the bare minimum that it needs to complete any specific computation. So this means you could have a data structure, and if parts of that data structure are not needed for a given computation, they may be unevaluated, and they exist in memory as a concept called a thunk, and then when you walk down your structure and need something, then it will be evaluated, only as it's needed. So this means that if I want to operate on an infinite list, as long as I'm not trying to evaluate the whole list, I can have that infinite list, in memory conceptually. And then I'm going to say something like, oh, take the first 10 items from this infinite list and do something. That's fine. We will evaluate those 10 items, but not the rest of the list. In a strict evaluation language, we would try to evaluate the infinite list, and your computer would lock up and just get hot and not ever do anything. Now, you can still make that happen in Haskell. You can try to actually evaluate an infinity of items, and the same thing will happen. But as long as the part that you're trying to evaluate is finite, you can use infinite data structures. And so we're going to use this infinity binding when we want to play with that aspect of Haskell. We have a couple of convenience functions. The $10 word that you will hear Haskell people use to refer to folds is, you don't need to understand this, but the word is catamorphism. And in other languages, you've probably seen folds referred to as reduce. So the idea behind a fold, and we'll see it in action, I promise you in this module, is given some data structure, boil it down to a simpler data structure. That's not an accurate definition, but I'm going to go with it anyway. Now we have these two flavors of fold, fold left and fold right. They behave differently in the face of infinite lists. And spoiler, we're mostly, if we use fold in this module, which we will, we're mostly going to be using fold right. And I will try and explain that when we get to it. All right, let's actually start filling in some functions here. Head or returns the head of the list or the given default. We can probably implement that very simply. Let's see, we need the first argument is our default, and the second argument is our list. So if someone passes in nil, we're going to return def val. And if someone passes in anything else, we don't need the rest of it, right? I think that's correct. Let's see if that actually compiles. I think this is actually a bug in the course because I didn't touch that. There we go. All right, so let's try this. Head or 3 nil should return 3. It does. Head or 3 5 attached to 6 attached to nil, right? Gives us 5, exactly what we wanted. So what's the point of this? There is a defined head function in the prelude for Haskell in the kind of built-ins, and it's not safe, right? Because if you try, and I don't know if we have head here, let's see. Right. In fact, let me be explicit here. We're calling data list head the built-in, and we're running it on the empty list. That creates a runtime exception. So it's really, really bad. All right, so first exercise done. Let's take a look here. The next one is product, the product of the elements of a list. So given 1, 2, 3, we should return 6 because 1 times 2 times 3 is 6. 4 times 3 is 12, times 2 is 24, times 1 is 24. So this is the first exercise where we can start to introduce some of Haskell's famous brevity. How should we do this? I'm going to show you this done the long way first, and then I'm going to do it the short way. And for the long way, I'm going to actually define a new function here. Right, so the long way to do this that you might think of doing this is, well, obviously I'm an experienced computer programmer. I know that they clearly want me to solve this in some recursive fashion. So I'm going to write an explicit recursive function, just like we were doing in our baby's first recursion video earlier. All right, so let's go ahead and do that. Well, if the list is nil, then we're going to return, let's see, this is product, so it's multiplication. So the identity value for multiplication is 1. And then if there's some value attached to the rest of a list, then we can return that value times, and now here we do our recursive call on the tail. That looks right to me. Let's see if it compiles. It does not. What did I do wrong? Incorrect indentation. Oh, I see. The indentation is because I removed that error. Interesting. I wonder why the optional thing is happening. All right, so we have this product 2. Let's test it on a list with 1, 2, and 3. We should get 6, and we do. Let's test it on 1, 2, 3, and 4. We get 24. That's fine, I guess. But if for everything we do, we're going to do this explicit recursion, that's a huge amount of cognitive load. I know someone up there is jumping up and down in their seat right now, shouting, "Oh, but recursion's easy. It's very straightforward. Just do it." No, that's a lot of code to do something that has a similar shape to the same thing that we're going to see every time, right? Just like it's why we want map to act like a for loop, right? So what can we do that's simpler? Well, let's say we have a list. We can use that fold right function that we mentioned above, that catamorphism. And in fact, let me go back and look at the definition of fold right to remind myself what the order of the arguments are. Okay, so fold right is right here. It's going to take 3 arguments. Asterisk, asterisk functions only take 1 argument. I don't want to hear it. It's going to take some function that takes an A and a B and returns a B. It's going to take some value of B, and then it's going to take a list of A. That's a lot, isn't it? Right? There's a lot going on there. I think of these as being 3 different conceptual values. It's going to take a function that does a thing. It's going to take a value that I think of as the accumulator, and then it's going to take the list that it's operating on. So what did I say? It's going to take a function, it's going to take an accumulator, and it's going to take some list that it's operating on, right? So the list, well, we have the list here. So that's right there. I'm going to remove the underscore. Oh, actually, this is an opportunity to take a look at holes. So let me do that explicitly. Well, let's trigger a bunch of error messages here. Yikes. Okay, we found a bunch of holes, which we knew because we put them there. So the first hole is for our function. And we can see because the definition of product returns an int, and we're putting fold in this function's context, suddenly this function is not returning A to B, is not a function of type A to B to B. It's a function of type A to int. So that's already helpful. The compiler is telling us that whatever this function is, its second argument at least is going to be an int, and it's going to return an int. Our hole is going to be of type int. Our accumulator is going to be of type int. So we don't know what that is yet. And we've got our list, and that's going to be of type list A0. I'm surprised that it's not list int, but I guess we don't know that yet. All right, so shocker, the list is going to be list. Now let's do this again, having saved this, and watch what happens to the type inference. I want to remind you that the hole for our list was list A0, some polymorphic value, and our hole for the function was A0 to int. But now we've replaced that hole with an actual list. And now suddenly our hole for function has changed to int. So that A0, now we have an actual concrete type that we're using. So type inference knows that it's this function. And here you could see it's trying to suggest a bunch of functions that are of type, potentially int, that might fit that hole. And it doesn't show all of them because that's potentially a huge list. Turns out none of those are what we want. So since this is product, now we can apply our own knowledge here. Since we know this is the product of the elements, the multiplication, the actual answer here is going to be multiplication, right? Now, we'll see if this actually works, because if we're taking type int here, maybe it wants a polymorphic number, but let's take a look, see what happens. Okay, so that actually took that. Now we only have this one hole, the accumulator, which is of type int. And since the operation we're doing is multiplication, the accumulator is essentially the first value, right? The accumulator corresponds notionally to this line here in our explicit recursion. So I want it to be 1 in this case. If we made it 0, then all our results would be 0. We'll reload it. There's going to be a bunch of failing tests here, but let's see, make sure the product test fails, or succeeds. I make so many mistakes. There we go. And you can see we did a number of tests, including the empty list and on these things, and we got the correct answer. And we could run that ourselves again by hand. Can we do like, let's do something more interesting. 120, great, and that works. So do I want to do this now? Yeah, I think I do, because what if I don't get through the entire list today? Let's show you one more way to do this fold. Let's call it product 3. Actually, I'm going to show you 2 more ways to do it. What I want to show you here is that for fold right, for multiplication, this is obviously really easy. Oh, you just use the multiplication function. But what if what you want to do to some list is more complicated than that? Well, Haskell makes it very easy to pass in a anonymous function, what we call a lambda function. So let's try that here. So we're going to introduce a backslash here, and we're going to say that this function takes 2 values, an item and the accumulator, and it's a function. It's going to return item times accumulator. I think that's right. Let's see if my syntax is correct. Looks like it is. Product 3. I gotta make it a little more interesting. All right, that looks correct. I'm going to show you one more thing, and this does not have anything to do with lists. This has to do with the currying and uncurrying of functions. So let's make a product 4. Okay, so let's copy product 3. Same implementation, right? Well, we don't have to explicitly, because this is so encapsulated, we don't need to pass this argument in at all. I've heard this called type-free or tacit programming. If we get rid of that binding, right, what's happening here? Well, we've got all this, and it's operating on a list. Named list. Well, how do we operate on that list if we haven't bound a name to it? Well, if you look at this and you remember the idea that any function can return a partial function, we can just remove that argument. And it looks like it should be like, what is this operating on? It's operating on nothing. Right? There's no list argument here. That should not work, but perhaps surprisingly, it does work. And the reason it works is everything's a function. If we call it with no argument, we get told, hey, there's no argument. But if we call it with an actual list, then it's simply like, literally you can view it as this code gets substituted for the name product 4. Okay, so I think I've hammered this home enough. So what can we do now as we go on? Well, now we've got sum. So I'm going to go pretty fast here. I'm not going to implement every version of this. We could do the minimal implementation of this, or a minimal implementation of this, right? Sum we can guess conceptually is going to be similar to product. We have product up here, right? In fact, let's take our simpler product that just does that. Right? And sum, instead of being multiplication, is going to be addition. And if we're going to be doing addition, then we know we don't want to start at 1, we want to start at 0, because the identity operator for addition is 0. And we could do this two ways. We could do that, right? Put list there. Or, like I just showed you, we could do this completely point free. Let's see if that works. Okay. Bunch of errors, but if we go up to sum, we can see here that our sum tests have passed. So conceptually, one way to think of fold right and fold left is fold left is a for loop. For left is when you want to do fold left is when you want to start doing some operation to every item in a list. Fold right also kind of accomplishes that, but conceptually what fold right does, and I want to credit Brian McKenna for this insight. If we're starting with a list that looks like that, then conceptually what fold right is doing, I shouldn't say conceptually, practically what fold right is doing is transforming that list into this, where your cons operator is being replaced by whatever function you have as the function, and your nil, the nil of your list, is being replaced by the whatever value you gave as the accumulator. Extremely powerful insight. And this, more than anything else, the fact that I could remember this is one reason why I tend to use fold right more than fold left, because this is very easy for me to kind of remember. All right, next one. Return the length of a list. So we could actually do this one with fold right. And I should say in Haskell, fold left is actually called fold L and fold right is called fold R. In the data.list types, we're using, variants of those with slightly different names because these are types. This is a type that was made for this class. All right, so can we just say +1? Well, I'm failing on remembering this. Let's actually do this similar to how we did product 3 and product 4, right? So product 3, we said item accumulator. The length here is going to be 1 plus accumulator. And then we don't need this item, right? We're going to kind of throw away the value. And I know there's a way to do this with the const function, but I don't think we've introduced that, and I don't remember the exact way to get it right. Let's see if this accomplishes what I wanted to do. And we are now passing the length tests. Okay, next we're going to do map. This is exciting. From A to B, a function from A to B, and a list returns a list. Okay, so we know, since there's two arguments here, don't at me, we know we can't do it completely point free, right? We've got a function and we've got a list. And maybe we can drop off that list. We'll do that later if we feel like it. And we know that fold right fold right is, have you ever seen that video of, I think the description I've usually seen is QA, engineer watching QA test things. Where does the circle go? In the square hole. And the engineer gets more and more upset because everything goes into the square hole. Fold right is going to be our square hole for this video. All right, so what have we got? We've got an item and an accumulator. We don't know what the accumulator is yet, but we're going to apply the function to the item and append it to the accumulator. And then that implies, so what does our accumulator have to be? Right? We're getting some list. It's of a polymorphic type. We don't know what it is. It's unlike our previous examples. It's not an integer, right? So what do you think our accumulator has to be? That's the question. In fact, let's do that there. Well, I think our accumulator has to be of type list, whatever it is. List polymorphic, list A. Let's see if we can look at the whole. And indeed, our accumulator is of type list B in this function signature. So it has to be the type of list that we're returning, but luckily for us, nil is going to be a valid member of every list. So the very first time through this essentially loop, accumulator is going to be nil, and we're going to prepend the first item onto it. And this should work as is. All right, list map, map, map. All three of our maps passed. Great, onward to filter. Return elements satisfying the given predicate. And so here we could say filter even on the list 1, 2, 3, 4, 5 returns a new list labeled that contains 2 and 4. Oh, and let me show you here, back up here. As I promised, we can make this point free and elide the list argument. Compiles just fine. Okay, so filter. We have some predicate. We have a list. I'm going to leave it off. Why not? Let's see if that works. And what do we use to solve this one? Well, we can put it in the square hole. That's right. All right. Item accumulator does something. I don't know what. And we know that we're dealing with lists here, so we know that the accumulator is going to be nil. And the predicate is going to take some item and return a list. So, and so I want to just take a moment here to make sure that the flow here in fold right is easy to understand. The implication here is that this argument that we're giving as the accumulator is the first time through the fold being passed in as this argument here. And then subsequent passes through, the accumulator, the argument, is going to be getting whatever this function returns. So we're kind of building it up as we execute. All right, so where were I? Well, we can just say if this is true, then we're going to return item appended to accumulator. Otherwise, we're just going to return the accumulator. And that is pretty brief implementation. It's probably not the minimal implementation of filter, but I think it's right. You're going to hear that a lot. I think it's right. I actually don't know for certain that I'm doing these right. I have taken this course before. The last time was several years ago, so some of this knowledge is still in my brain. But, you know, if I make mistakes, I make mistakes. I do edit out the mistakes where I spend 20 minutes staring at the screen going, what should I do? Because that's not interesting for you to watch. But for the most part, if I make a mistake and it doesn't interrupt the flow too bad, I'll leave it in. All right. And that's because, you've heard me say this many times, mistakes are how we learn. All right. List, filter, filter even. All of these tests passed. Let's just do that really quickly. Let's test it. Filter, even. Just to see it ourselves. We got back 246. And if we were to do the same thing, but with odd, 135. Great. Let's move on. Append two lists to a new list. This is the first exercise in this class that is tricky. And the reason it's tricky is if you're doing this kind of without any help, I really encourage you, by the way, to try to do these before watching this video. Like, that really, watching me do it doesn't get you much. In order to learn, I think you really need to try these. So if you've just been watching me and listening to my dulcet tones, please stop and go actually try these yourselves and then come back. Our tests here for lists append test with very long lists. And in fact, they test with infinite lists. So this is really the first exercise where trying to attack this in the naive way by just writing a recursive function is going to hose you. Your function, assuming you try it, will work fine on the trivial case, and then on the infinite list case, your computer will lock up. I'm not going to do the naive implementation here. The first time I went through this class, I definitely did. So don't feel bad if you did. I think that's normal. What should we use to solve this problem? Well, I think we should put it in the square hole. We should use fold right. And what should we put into fold right? Well, we've got two lists. We want the first list to be appended to the second list. So if the first list is nil, our answer is just the second list, right? That's equivalent to the case where we never execute the code, kind of, inside our fold. So therefore, our accumulator is going to be our second list. And our first list is the thing that the fold is going to operate on. And so that means that this, I think that's the solution. Let's look. And our append worked, including in the infinite cases. And we can see that, when we run that test by hand, we get the results that we expect. My streaming setup is starting to act up, and I don't know if that's a sign of technical problems or if it's a sign that lack of coffee is making me forget whether I'm recording or not. But let's do one more. Flatten a list of lists to a list. So given three lists, it's a list of lists, one list with three lists inside it. And then it's being flattened to just a single list. And we can see that our tests here are going to involve infinite lists. So it's going to be easy to make a mistake. Well, I'm going to keep making the joke. I'm going to keep making this joke until people are commenting in the comments, begging me to stop. This takes one argument, so let's be creepy and do it in a point-free way. We'll put it in the square hole. And remember what I said earlier about the effective semantic that I learned from Brian McKenna, that fold right, you can think of it as replacing the cons operator with some other operator? Well, we can flatten by just using the append operator. And I think that's going to work. We use nil as our accumulator because that is the, because this is a list we're operating on. Let's see if that works. You know what, let's do this test by hand, just because I think it's interesting to look at. In fact, what happens if we just evaluate that? Okay, so that's what it looks like in kind of your more familiar list format. And we get the result that we expect. And we can run the tests just to make sure that the infinite case work as well. And there's our flatten. All right, what's next? Map a function, then flatten to a list. Well, so here, maybe we don't need to use the square hole. We have, it goes from A to list B, it takes a list A, and returns a list B. So let's, despite my using point-free syntax to be cute, I almost always want to have the arguments there. Even if I then remove them later if I want to do it point-free, because it helps me think about it. Some people would argue with that. Some people would say, well, you shouldn't have any names that you don't need, and it'll be easier to see the shape of the code. This is how my brain works. I think that we can do this by composing flatten and map. Right? We can say, let's do it from the inside out. Map function on list A, and that should give us this list of lists, and then we can say flatten, right? I think this is the naive solution. Let's just make sure it compiles. It does compile. That test passes. There are, kind of the motto of Haskell is there's more than one way to do it. There's more than one syntax. And so one way to do this, I'm going to do a bunch of these. All right. $, to remind you, is just function application, space, but with a lower, different associativity order. Yeah, a different precedence is the word I was looking for. So that'll compile. I don't know why I decided to do everything there. I just keep trying. Okay, that looks like that works. We can do something else though, right? Can we do this? Let's see if I got that right. Seems like I did. If we could do that, we can do this. Is that right? We might need parentheses here around that map fn. Guess not. Okay, so you can see here, you can get as brief as you want to get. My personal taste runs, somewhere in here. Composition is very powerful. I think it's the first time you've seen that dot operator. That's simply composing two functions together. Composition can be very powerful. I also find it somewhat confusing sometimes because I am a bear of little brain. So I will very often lean towards the more explicit parts, the more explicit ways of phrasing these things, simply because it works better for my brain. Flatten a list of lists to a list again. However, this time, use the flat map function that you just wrote. Okay, so flat map takes a function and operates on a list. All right. So let's put a hole there for right now and intentionally get the compiler to tell us what it's missing. So a function from list A to list A. So this is kind of weird, right? Flat map is flatten and then map. Flatten is what we want. Like, literally, flatten is what we want here. But flat map wants to map something. So we have to apply some function to all of these lists that are inside it, right? So let's do something we know will not work. Okay? What would happen if we flat mapped sum? In fact, I don't need parentheses. What would happen if we do that? Oh, because it's polymorphic, sum is not polymorphic. Sum wants to do I have anything else I could use here? No. So we want something that is going to take any type of function and return something of the same type. I want something that's maximally polymorphic. And there are very few functions that are like that. We essentially need to apply some function that goes from A to A, given any data type. And there's really only one function that does that, and that is the identity function. Seems to have worked. Our list of passing tests is getting very, very long. Seek optional. Sequence optional. Convert a list of optional values to an optional list of values. This one. I think, do I want to skip past it or do I want to cut? All right. I'm declaring what's going to happen here now. Functions we have left: seek optional, find, length GT4, reverse, produce, and then not reverse. So I'm going to tell you from experience that seek optional, sec optional, I don't know how it's pronounced, is the hardest thing in this module for me to understand. It's so hard that even having done it and knowing what the implementation is, I don't think I can do a good job of explaining this to you. So here's what I'm going to do. I'm going to break the video here. The next video in this series will be finishing all of the rest of list. We're going to do find, length GT4, because these are a little more interesting than the ones we've been doing so far. So we'll have a video just for those. And then I'm going to have a third video where the only thing we do is seek optional. And I try to wrap my brain around what exactly this is doing. And hopefully I will learn as well as you. It's entirely possible that you will get it before I get it. But that's what I'm going to do, because I want this to be a learning experience for me as well as you. So that's my goal. I'm going to call it here. This video is getting too long anyway. I'd like to thank you for joining me on this journey. Schedule-wise, these things go up as soon as I record them. The day after I record them, I put them up for my early access viewers, and then they slot out where all the videos go. Basically, I publish to the public one video a week on Fridays, usually Friday morning. So that's the schedule. If you are dying to see these before they go public, please join the channel as an early access member, and I would love to have you on board. Thank you so much for joining me. This has been Tea Leaves Programming. We're programming like it's 1979. You're watching Haskell for Dilettantes. Thanks for joining me.